Hey everyone, welcome back to Forge College. I'm absolutely thrilled you're joining us for this explainer. In our last lesson, Foundations of Distributed Systems, we laid down the groundwork. State replication, networked peers, fault tolerance, the whole shebang. But here's the thing. If we really want to understand why modern systems, like blockchains, are built the way they are, we can't just look at how they run today. Nope, we've got to dig into the spectacular, messy, historical failures that practically forced engineers to invent them in the first place. So, today, we're taking a super fascinating, and honestly kind of chaotic, journey through the history and evolution of distributed systems. All right, here's our game plan for this time-traveling trip. We're going to kick things off with a mental model we're calling the choir and conductor, then we'll dive into early networks, check out the RPC illusion, scale up with web-scale replication, witness the rise of consensus, and finally, wrap it all up with trade-offs and future. So let's jump right into Section 1, the choir and the conductor, a mental model. To keep all this dense technical history grounded, I want you to imagine a choir. They're all singing from a shared musical score. Notice how perfectly this maps onto the nuts and bolts of distributed computing? It's like a giant puzzle fitting together. The individual singers, those are our nodes, the separate computers sitting out there on the network. The sheet music they're all reading from, that's the system state, the shared data that literally everyone needs to agree on. And the conductor standing up at the front, keeping the tempo, that's our coordination mechanism, basically the leader of the system. Moving right along to Section 2, early networks and the time-sharing era. Let's turn the clock way, way back. If we look at how this tech evolved over the decades, we start at Phase 1, time-sharing. And as we progress down this timeline, you're going to see how the very specific, massive headaches of each era basically shoved us into the next one. We'll go from time-sharing through distributed operating systems, hit web-scale scaling, and finally land squarely on modern decentralized ledgers. Now, in the very beginning of computing, physical resources were massive. They were scarce, and man, were they expensive. You didn't have a sprawling choir spread out across a stadium. You had a tiny group crammed into a single, highly expensive room, completely relying on eye contact just to stay in sync. Time-sharing was a total game-changer here. It maximized those limited compute resources by letting remote terminals talk to a central server through simple message passing. Suddenly, multiple users could share one giant machine. But there was a massive catch. It completely failed at fault tolerance. I mean, if someone just tripped over the power cord of that central mainframe, every remote terminal went completely dark. The entire choir was silenced in a split second. Which brings us perfectly to Section 3, the RPC illusion, hiding the network. That massive vulnerability, combined with the wild complexity of trying to connect separate machines, forced engineers into our next era. Because let's face it, programmers were getting incredibly sick and tired of dealing with the sheer messiness of the network. So they invented an abstraction, and they called it the Remote Procedure Call, or RPC. Think of an RPC as, well, it's basically an engineering magic trick. It lowers programming costs by making remote network calls over a wire feel like they're just local actions happening right there on your own machine. For our choir, this was a super ambitious attempt to just pretend the network was absolutely perfect. It was like pretending all the singers were magically standing shoulder to shoulder, even when they were actually miles apart. But here is the harsh reality of magic tricks. Eventually, the illusion shatters. Abstraction absolutely solves immediate complexity, but it completely shifts the heavy lifting over to failure handling. RPCs hid the physical reality of the network right up until, say, a rogue backhoe accidentally sliced through a fiber optic cable somewhere. Because, as we all know, construction equipment is the natural predator of the internet. Suddenly, parts of the network just couldn't talk to each other. RPCs turned these network partitions into a first-class programmer nightmare simply because the system had absolutely no idea how to handle singers who literally couldn't hear each other anymore. Okay, let's roll right into Section 4, web-scale replication and global networks. The sheer unreliability of networks led us directly here. The internet was exploding. Suddenly, our choir wasn't just a few people in a single room. It was massive. It was dispersed across continents and highly, highly prone to breaking into separated sections. Which leads me to a very serious question. What actually happens when the choir simply cannot hear the conductor? I mean, really think about that for a second. Half the singers are literally locked out of the concert hall because of some unpredictable network latency. What on earth does the system do? This very real, very painful dilemma
is what we call partition tolerance. When you design systems that span the entire globe, you absolutely must design them to survive physical network separation, because the network will inevitably split. It's not an if, it's a when. And when it does, the system is forced into a very uncomfortable choice. Do we completely stop the song, or do we just keep singing, even if it means we're going to sound terribly, terribly out of tune?
This right here forces a strict trade-off. On one side of the ring, we have availability. This is the show must go on approach. The local singers just keep belting out their parts, prioritizing user-facing speed with a plan to sort of fix any wrong notes later on. We call this eventual consistency. On the other side, we have strict consistency. This approach demands that we stop the music entirely. If literally everyone's sheet music doesn't perfectly match up, we halt the entire system until we can guarantee absolute correctness. No exceptions.
And that strictness brings us to Section 5, the rise of consensus, guaranteeing order.
For a long time, web services heavily favored availability. They just wanted your web pages to load blazing fast. But as systems started holding critical, high-stakes data, think financial transactions, singing out of tune, that was no longer an option. They needed absolute correctness, which ushered in the strict rules of consensus protocols. Now, the absolute crucial takeaway here is that every single historical milestone was a direct response to a very practical engineering pain. Timesharing used remote terminals to solve limited compute. Distributed operating systems use RPCs to cure programmer pain, and web scale services relied on replication to handle massive concurrency. Each mechanism was really just a stepping stone. So, to solve the modern need for absolute, unbreakable correctness across a scattered network, engineers created the consensus protocol. These are mathematically strict algorithms. You might have heard of famous ones like Paxos or Raft that maintain a single, totally ordered log of state changes, even when individual nodes crash and burn. Jumping back to our metaphor, this is a strict single conductor guaranteeing that every single singer in the choir sings the exact same note in the exact same order. No improvising allowed. Here is exactly how this leader-based consensus works sequentially in 3 steps. Step 1, assign a leader. A central conductor takes charge and issues the cues. Step 2, replicate state. The choir meticulously copies down the new sheet music. Step 3, achieve total order. Everyone executes the action perfectly in sync. But notice the trade-off here. While it absolutely guarantees perfect order, getting literally everyone to agree costs precious time and brings massive communication overhead. Achieving perfect harmony actually slows the whole system down. All right, let's bring it all home with Section 6, Trade-offs and Future Modern Ledgers. This finally brings us to the present day, the modern era of distributed ledgers and blockchains. This is a technology that takes all of these hard-fought historical lessons and synthesizes them into one architecture. Let's do a quick review of our key takeaways. First, historical milestones always respond to hard hardware and network constraints. Second, while abstractions like RPCs make our lives way easier, they hide failures that inevitably have to be dealt with. Third, the trade-off between availability and consistency, that is basically an unavoidable law of physics when networks partition. And finally, global blockchains take all these historical replication models, sprinkle in some advanced cryptography, and add a brand new absolute game changer of a feature: trust minimization. I really want you to remember this quote. Historical milestones in distributed systems are best understood as responses to concrete constraints. Whenever you're studying Web3 and you come across some wildly complex new feature, just remember, it doesn't exist just to sound highly technical or fancy. It exists to solve a very practical, real-world problem that engineers have been battling for decades. So as we wrap up this explainer, I want to leave you with a bit of a provocative thought to prime you for your next steps. Whenever you're evaluating a real-world blockchain or distributed ledger, ask yourself 2 things. Who exactly is the conductor in the system? And what happens when the singers inevitably hear their cues late? Honestly, answering just those 2 questions will immediately reveal the hidden trade-offs of any system you're looking at. Well, thank you so much for joining me on this explainer today. It has been an absolute blast walking through this wild history with you. To keep exploring these concepts and to learn more about how these historical trade-offs shape modern Web3 design patterns, make sure to visit forge.college. Check out all the other awesome educational resources we have over there. Keep asking those big questions, keep learning, and I will see you in the next one.